So in the larger context of the electric power system, the term load can have several different connotations. So far we've been using the term load to refer to a single device, such as a vacuum cleaner or a light bulb or a computer. In the big context of the power systems, though, individual devices really aren't that important. More frequently, load is modeled in aggregate. Rather than considering just an individual appliance, load is going to most often, in the context of electric power system, refer to an entire household, a city block, all of the customers in a certain region, et cetera, et cetera, et cetera. The collective behavior of all these appliances and machines working together, right? So therefore, in the vocabulary used by electric utility engineers, the term load has attributes beyond a simple impedance, like we've shown before, that relates to aggregate behaviors, most specifically, or most importantly, I guess I should say, the timing of when these devices and customers use electric energy. So that becomes very important. You know, so far we haven't looked at when devices use electricity. We've only looked at you know, their load model, in essence. What's their impedance? A customer's usage of electricity is going to change daily and seasonally, and this really reflects human schedules and weather patterns. You know, your electricity usage as an individual in your home really is reflective of when you are in your home and what the temperature outside is. Because we have few methods to store electricity, utilities must produce it at the instant it's needed, and what we mean by that is they must always be balancing supply and demand. So therefore, the electric industry has to be very responsive to your individual needs as a human and your usage patterns. So in the language of the electric utility industry, we call that term demand, or the instantaneous need for electricity. So what is my customer's demand? So we have this kind of new term that we're going to use called demand. And the demand really is, what is the aggregate instantaneous need for electric energy from some group of customers? That could mean an individual customer, that could mean a substation, you know, can have different meanings in different contexts. Energy use, on the other hand, is total amount of measured electrical energy that is consumed over time. So whereas demand is really a power, right, it's in kilowatts, energy use is in kilowatt hours. It's how much energy did I have to supply my customer over the week, or over the day, or over the course of the month, right? So that we have these different terms. The plot of electric power demand on a utility as a function of time of day is known as a load curve. So load curve, I've got time on this axis, and you can see I've got power on the y-axis. This can represent electricity demand by an individual or an aggregate load. In these diagrams, we are presenting two load curves. One is for an electric utility for a summer day, or a summer day during the summer, I guess I should say. It's not just during the day, it's a day that occurs during the summer. And then one for a winter day. The reason we do that is we want to show that these are actually representing aggregate loads at utilities, and we can see that at this utility, during the summer, their peak load occurs kind of in the late afternoon, and it's almost 9,000 megawatt hours is how much electric demand this utility has to serve. We come here to the winter, and kind of in the same, at a similar time of day, they're only serving about 8,000. So about 1,000 megawatt hours less. Same customers, right? These are the same customers. This is just the customers using electricity during the summer, and this is the customers using electricity during the winter. So not only do we divide it between seasons, which is very common, we also take the demand during the course of the day and we categorize it between base load here, which is this kind of dark red. The orange is called the intermediate load, and then this yellowish color is called the peak load. And you can see we've done the same things, just using different colors on the winter day. The reason this is done is primarily to determine the type and quantity of power plants that are going to be utilized to produce the electricity at the right times. Different power plants have different characteristics that are suitable for different operating scenarios, and we have to match those power plant characteristics with the power demand of the customers at any given time. So we see much of the demand is continuous, which we call base load. It's the value below which there isn't a whole lot of electrical demand fluctuation. This kind of load is typically met through big coal-fired power plants, nuclear power plants, natural gas power plants, and hydroelectric plants. These types of plants typically can produce lots of power, but cannot change the amount of power that they output very quickly. You kind of bring it up, it'll output a lot of cheap power, but it isn't going to respond very dynamically. It's got slow ramp rates, we would say. Intermediate load here is often met with the use of smaller combined fast-acting plants. These might be combustion turbines, for example, or smaller natural gas turbines. And the electricity produced by these isn't going to benefit from the benefits of scale that base load does. So this electricity, it actually costs a little bit more to produce, and I'm willing to pay a little bit more because I can ramp these generators up and down faster than I can the base load generator. So they're a little bit more responsive, so I pay for that. Well, peak load is almost exclusively delivered by combustion turbines. You can see that there's a lot of, the slope of the curve here is really, really peaky, really, really steep. So we've got to be ramping these generators up and down, ramping them up and down relatively quickly, turning them on and off relatively quickly. And this is the most expensive type of power. The other way that this is met is sometimes we use load management techniques such as demand response, where we shut off HVAC systems for brief intervals to kind of meet these loads. Notice that if you integrate this load curve or add up all the area under the curve, you would get total energy consumed by the load, or the aggregate load in the case. Curves like this can be drawn using data for a single day, data averaged over a week, over a month, over a year, and really the purpose of charts like this is to show the time-dependent behavior of when electrical loads demand power for a certain utility, so that you can plan your generation during the different times of the year. You need to make sure you have enough coal, that you've got the contracts in place and things like that to purchase the fuels, that you have big enough generators to meet the predicted load and things like that. So very important, the ideas of demand and load curves. Another way to look at that load data that we just presented is what's called a load duration curve, which is a plot of the percentage of time a load is at a given demand level. The electric demand is plotted on the vertical axis, and the percent of occurrences are plotted on the horizontal axis. So you see here what we've got is we've got an electric load, the percentage of the year that the load is at a certain demand level, and then we've got demand level on the y-axis here. So you see from this plot, I come over here and I see that the demand for whatever system, whatever aggregate system we're representing, really never drops below 2,000 megawatts for this system. For 90% of the year, it's at 3,000 megawatts or above. So for most of the time, it's at 3,000 megawatts or above. For half the year, it's at 3,500 megawatts or above. And really what we see is we can start seeing, well, what do we consider base, and what do we consider intermediate, and what do we consider peak? And you can also see by what types of generation that we serve that load. So again, for base load, coal plants, hydroelectric, nuclear, renewable energies. Intermediate load, we've got combustion and purchased power. And then for peak, we've got these small peaker plants, which are combustion turbines. And purchased power just means we're buying power from neighboring electric utilities, right? So we've also introduced two new terms here: reserve capability and electric demand. Electric demand is how much demand there is on the system by the customers. Reserve capability is, well, it's the difference between what my base, in this case my base load, can provide, which is about 3,100 megawatts, and how much is actually being used. So what that's saying is my power plants, my base load power plants, are capable of producing 3,100 megawatts of power, and at some time, during part of the year I'm not even using all that, or part of the day I'm not using all that, so I can sell that off. It's my reserve capacity. Same for intermediate load. I've got this intermediate that's able to, supply, I don't know, that number looks like 4,800, and that's 31, so 1,700, about 1,700 megawatts. And I'm not asking 1,700 megawatts of my intermediate load there, so sometimes I have this extra reserve margin, and so this is just called reserve capability. So load duration curves are, in this form, are really, really commonly used for system planning. The behavior of loads, like we said, can be viewed in aggregate, but to get aggregate information, usually what we do is we start looking at individual customer loads. The figure that we've got plotted here presents a customer demand curve for one individual, which is a plot of his instantaneous kilowatt load of a customer plotted as a function of time. To define this load, the demand curve is broken into equal time intervals, and a customary interval in the electric utility industry has been historically about 15 minutes. In each interval, the average value of the demand is determined. So for a 15-minute interval, I will integrate the energy, I'll divide by the time interval, and what that gives me is this average value of demand in kilowatts or megawatts or what have you. This straight line then represents the average load during that 15-minute time interval. You might say, well, why don't I just take the exact load value or demand value at any given point? Why don't I just use that information? Why am I even averaging it? Well, historically it's been very difficult to collect that kind of information from customers. Think about your electric utility. They actually only measure how much energy you used, and they measure that data point once a month when they read your meter. So even getting 15-minute intervals from all the customers in the electric utility industry has been relatively difficult. And also smaller intervals, they require more complex and expensive data acquisition tools, so we're going in that direction in the electric system with smart grids and smart meters. But when utilities are doing load studies, typically they use this 15-minute windowing. It's called the 15-minute kilowatt demand. It's kind of got its own name, 15-min kilowatt demand. Right, and that's that 15-minute window from 6:15 to 6:30, for example. So this plot that we have here shows 24 hours of 15-minute kilowatt demand information. And this really actually does represent a typical residential customer. So each of these bars represents 15 minutes of kilowatt demand data during 15-minute intervals over the course of the day, right? You'll notice over the course of this day, there's great variation in the actual demand as measured by this 15-minute kilowatt demand metric. For example, there's only 3 times during which the kilowatt demand exceeds 6 kilowatts. So here's 6 kilowatts, and I see it exceeds it here, here, and here, right? The largest of those excursions is called the 15-minute max kilowatt demand. That's actually this one right here, 15-min max kilowatt demand, right? It's the biggest, right? In this diagram, it's 6.18 kilowatts, and it occurs at the time of day 13:15 military time. And I've just recreated that graph right here. During this 24-hour period, energy is consumed, right? I can calculate how much energy is consumed by multiplying the 15-minute kilowatt demand by which is measured in kilowatts. So if I want it in kilowatt hours, I measure it by 0.25, right? Because there's, 15 minutes is a quarter of an hour. Kilowatt hour, or the energy usage, is just going to be 15-minute average demand. Times 0.25, right? Because 15 divided by 60 is a quarter. That'll give me my energy in kilowatt hours. So the total energy for the day is therefore the summation of all the 15-minute interval consumptions. I could say energy total is just going to be equal to 0.25 times the summation from n equals 1 to, let me do some quick mental math. I've got 15-minute intervals. There are 4 of them in an hour, 96 15-minute intervals in one day of just this 15-minute kilowatt. All right, if I just sum those all up, all 96 of those little data points, if I just sum them up and multiply them by 0.25, I'm going to get my total kilowatt hours used during the course of the day. So for example, if I were to do that for this chart, I don't have all the data points exactly on here, but I did the math from the spreadsheet that I used to produce this, and this plot's going to give me 58.96 kilowatt hours. Of electric energy consumed by this customer over the course of a single day, right? We can then average this, right? That he used 58.96, or she used 58.96 kilowatt hours in 24 hours. So if I divide that number by 24, I'm going to get the average demand. It's going to be 58.96 divided by 24. And that's going to give me 2.46 kilowatt hours. So now I've got my 15-minute average, I've got my daily average, I've got my max 15-minute demand. I got a lot of different things that I can begin to quantify consumer consumption behavior with. Primarily the reason we do this is we're trying to calculate what's called load factor. It's a term that is used to describe the variability in a customer's load profile. And it's defined as the ratio of the average demand to the maximum 15-minute demand. And really what it does is it gives an idea of how well the utilities facilities are being utilized. Clearly, an optimal loading factors it would be 1. And how we calculate it is we just take the average 15-minute kilowatt demand and we divide it by the max. So before we did 2.46 kilowatts. That was the average demand, right? We summed all this up over the course of the day, divided by 24. And then we divide it by the peak excursion, which remember we show is that. So 6.18. And we get a load factor of 0.4 for this. Not a great load factor. We can see that, the average electricity consumption for this person is, about right there. And there are some pretty big excursions, which means, all the money that was spent for transformers and everything to supply that 6.18 wasn't getting utilized. It was a capital expense that wasn't making the electric utility much money. High load factors are actually, while one would be ideal from a utilization aspect, doesn't give you any room for growth, right? So you can't ask for any more energy to be delivered to customers or power to be delivered to customers if you've got a load factor of 1. So they typically don't want to operate at a load factor of about 1. Typically, multiple customers are going to be connected to the electric grid at a single point. For example, in a residential system, the transformer used in this application would be a distribution transformer. It's a step-down transformer used to convert the distribution level voltage down to a level appropriate for customers, and typically you'll have like usually three customers connected to that distribution level transformer. Each of these multiple customers connected to a single distribution transformer, they're going to have their own demand curve. Right? Each of them is going to look a little bit different based on their own individual behavior of teeth brushing with electric toothbrushes and DVD watching and such things. And they're going to be all kind of similar. Well, they're all going to be kind of similar to this, but they're all going to be unique in their own timing. Right? Well, what will happen is, since they're all connected to one transformer, we get aggregate behavior, where all the variations add together. So here's some example data for 4 different customers. What we've got is we've got customer 1, customer 2, customer 3, and customer 4, and they all have different energy usage. Remember, that's the total amount used over the course of the day. They've got different peaks. That's the biggest one. They've got different time that that peak occurred, right? They weren't what we would call coincident. They all occurred at different times. And then they've got different averages, right? And then also different load factors. We've got a relatively low factor. We've got a really great load factor of 0.81 here. So how does this data combine? Well, what we see by this graph, which is the combined demand curves, 15-minute average demand curves for these 4 customers, we see that the aggregate behavior is substantially different than that in an individual customer in both magnitude and temporal variation. In fact, although the magnitude will generally increase, fluctuations in the time when electricity is used will tend to decrease. When we sum the 15 kilowatt demands for each time interval and we aggregate for several customers, this is called diversified demand. This graph is diversified, just meaning it's been spread over several customers, right? And it gives data on the loading of the individual transformer used to serve that particular customer grouping. You'll notice from this sample data presented for these 4 customers that the demand curve is really beginning to smooth out as compared to an individual customer's demand curve. I'm just going to flip back real quick. Look how peaky this one is. There's huge excursions. In this one, there are still excursions, but the magnitude of the excursion compared to the average level has been reduced. So we could see that the 15-minute maximum diversified demand here, it looks like it's occurring at, right about here at, 17:30 or 5:30 in the afternoon. And it's got a value of, a little bit more than 16 kilowatts, 16.16 kilowatts is what I have written down for that, 16.16. That max demand and time doesn't correspond with any of these times, right? The maximum diversified demand does not necessarily occur at the same time as any of the individual maximum demands, nor is that maximum demand there the sum of these max demands, right? We have to consider both the magnitude and the time. We can also plot a load duration curve for diversified demand, similar to what we did previously for the aggregate load, right? Typically, a load curve is going to plot these 15-minute kilowatt demand versus, again, the percentage of time that the loading occurred over. And really what this is done with transformers is it really determines whether a transformer needs to be replaced due to an overloading condition, right? A transformer will be able to serve a certain amount of power. And you want to know how close to that operating limit, what percentage of the time are you really operating near that limit. So these charts are very, very commonly used by distribution planners to determine whether or not they need to increase or add new transformers.